Hello everybody, I'm Hadley from VCC Team 61, along with my teammate Frank, and we're both recent alumni of FTC Team 8581. And so here's our VCC locking Mecanum Drivetrain. And before I explain how this drivetrain works and a little bit about the design itself, I'm going to explain the history of the concept here. So, most modern FTC games have required high agility over high traction. So most teams have decided to use Mecanum wheels, and they've been really effective. These are some examples of cool or really competitive designs over the last few years. But Mecanum wheels do have some, and have had some disadvantages in the last few seasons. An example being maybe the balancing stone might have been a bit more challenging with Mecanum wheels versus traction wheels. And so, for that and other reasons, some teams pick six-wheel drive instead. And six-wheel drive also has it has more disadvantages than Mecanum and FTC for the most part. But they can track really straight. They have excellent traction and climbing ability, and they negate the need for odometry modules if you're into that kind of thing with Mecanum wheels. And if you add a turret to it, as Data Force proved last season, that makes up for a little bit of the lost agility. And so there are some drivetrains that people have worked on in FTC that try and combine the agility of Mecanum drivetrains and the traction of six-wheel drive drivetrains. And all of these have had pretty limited competitive success. And the first type I want to talk about is coaxial swerve drive. So here are some examples of coaxial swerve drives that were used on competition robots, or robots that were going to be intended for competition in the case of Cybots. And the downsides are the update rates on the Rev Hub just aren't super fast. Finding suitable servos is difficult, and the current draw on coaxial swerve is really high, making it generally not a very favorable candidate. It also can't strafe instantly like a Mecanum drivetrain. And the next and more kind of upcoming and popular version of swerve, differential swerve. Here's two examples of FTC scale differential swerve Filobots over there used in competition, and it has a really low ground clearance for the most part in FTC designs, and that can be a disadvantage in some games. I'm sure you could find a way around it, but it's also a very complicated drivetrain to program and control. But you don't have to worry about the servos. It also can't strafe instantly, like Mecanum drivetrains. The next one is ball drive. As far as I know, there's only been one ball drive used in competition. It has a really weird motor setup with only 3 motors. Instead of usually you'd put 4 on your drivetrain. And so you're not getting the max motor efficiency there. It's gigantic, and from what I gather, there were some slipping issues with the wheels on the balls, and that could be problematic in some games, particularly in autonomous. But the drivetrain had decent strafing ability, decent traction, and climbing ability as well. But it's really complicated to manufacture and is really big. And the next type of drivetrain that, as far as I know, again, there's only been 2 versions that have ever been used in competition, and it is Octacanum. And so we have Nerd 1 from 8371 on the right, and we have the Cafe Bot Octacanum drivetrain from Block Party on the left. And the Block Party one, the drivetrain was really big. It did not work well because Tetrix gears and Tetrix motors. And then the one on the left, Nerd 1, was just really gigantic, and the team ended up spending a lot of time on the drivetrain and not as much time on the scoring mechanisms. But the drivetrain did shift. It could switch between traction wheels and Mecanum wheels. And so in the past, I've physically or in CAD designed and worked on all of these types of drivetrains: coaxial swerve, differential swerve, ball drive, and octocanum, as well as Mecanum and regular six-wheel drive robots. And from this experience and talking with people in the FTC community, I think of all of the exotic drivetrains out there, the one that would have the most potential to be competitive would actually be octocanum. And that's because you have the benefits of Mecanum wheels and the benefits of traction wheels, and you have both. But the biggest issue is, as you see, they are both gigantic drivetrains, and they take up a lot of real estate that you could be using for scoring mechanisms. And so I started thinking last year in 2019, well, what if you had a wheel that could be a Mecanum wheel and a traction wheel at the same time? And so I started doing some research on this, and I ended up finding this video from FRC 3026 Orange Crush. And so, oh wait, nope, I want to play the video. There we go. So they have this brake in here, and as you see, the rollers move, and then when you push on this plastic brake, it stops the rollers from moving. So I thought, hey, this is really cool, and it seems like it could be relatively easy to make an FTC scale version of this kind of brake. And in this case, on FRC 3026's drivetrain, they actuated the brake using a pancake cylinder, pneumatic cylinder. And in FTC, we don't have pneumatics, but we do have servos. And what you would typically use pneumatics for in FRC, we use servos for in FTC. So I was thinking, well, let's start working on a braking Mecanum drivetrain, a locking Mecanum drivetrain that uses a servo and a linkage to kind of push the brake in and out. And so I started on this design here in the fall 2019, and it just ended up being kind of cumbersome, and I never quite finished the design. I wasn't really that happy with it. And then later, in winter 2019 and maybe early spring 2020, I started working on a version that would not be FTC legal and would use a custom pancake hydraulic cylinder, because I was interested in working with hydraulics maybe. And I was getting ready to prototype the cylinder and stuff, and then the whole COVID-19 pandemic happened, and I had to come home from college, and I didn't have access to the tools to manufacture the cylinder anymore. So I just kind of shelved the project for a while. And then I heard about the VCC competition this summer, and I was like, oh yeah, well, give it another shot and make this version FTC legal. And so that is how I ended up with the current drivetrain. Locking Mecanum 3 is what we call it. And here it is. It's a pretty nice looking drivetrain. Frank did all the plates. Get to that later. It's pretty cool. And it can be broken down into three main subsystems. We have the structure, we have the wheels, and we have the odometry modules. Then the wheels themselves can be broken down into two subsystems. And those subsystems would be the braking system here and the power transmission system from the Neverest motor over here. So now I'm going to explain how the wheels themselves work. So I'm going to start kind of by building this from the ground up using visibility settings over here. So the entire wheel is based around this 9mm shaft. So this is a 9mm round here, and this is 9mm hex. And it would have to be custom machined and stuff. It's kind of a complicated shaft. And so it has these slots in it. And these slots guide the linear actuator that engages the brake. And so let's turn on some of this stuff. So we have a compression spring, and then we have, there's a roll brake. Ooh, gotta expand this. Ooh, there we go. brake plunger. And so we have a plunger in there that is the diameter of this hole, and it is preloaded by this spring over here, so it's being kind of pushed out this way. And then you have the servo, which we'll eventually see drives a screw that pushes this in and out. And then this is connected to what I call the brake hub right here, with some 2.5 millimeter screws, if I can find them. There they are. And so this can slide in and out 2 millimeters of travel. And so that is the beginning of our brake actuator here. The next part of the drivetrain is an in-wheel gearbox. For a long time, since I kind of learned that was something that was possible, maybe back in relic recovery, I've been interested in in-wheel gearboxes. I've kind of played around with the designs, and so this is just kind of a standard in-wheel custom gearbox. And it's VCC, so I don't have to worry about buying all the parts. And so it's right here. And it's a dead axle gearbox, so the ring gear actually spins around this shaft. This is a dead axle shaft, and then your input from the Nevros motor over here is this HED3 pulley. And the pulley plus the gearbox has a total reduction of 18:1 on a 4-inch Nexus Mecanum wheel, so a pretty standard ratio. And so you can imagine the wheel is attached to this, as we see over here. And so we have to push a brake into the wheel without locking the entire wheel, because we don't want to break the entire wheel, have the wheel stop. We just want to stop the rollers. And so the way I came up with to do that is to have the brake pad on bearings. So as you push in and push against the rollers, which would be up here and down here, the brake pad spins with the gearbox and the wheel. It looks like I'm running out of time on this video, so I'll get to that in the next installment. Hello, I'm back for part 2 of my series on my VCC Team 61's locking Mecanum Drivetrain. So before the end of the last video, I was talking about how the brake pad needs to be on bearings so it can roll with the gearbox here, which is attached to the Mecanum wheel. That way you don't stop the entire wheel, you just stop the rollers. And so here's some 15mm deep groove bearings, and then I also have a hub bearing in here. It's just a polymer bearing to make sure the actuator here moves smoothly along the 9mm shaft, and a spring clip to retain it all, or a retaining ring to retain it all. And then we have the brake wheel, which is pressed into the bearings, and the brake tread, which would just be a hard durometer, polyurethane, or we'd have to play around with the durometer to figure out exactly what would work best with the Nexus rollers. So this is the main inner wheel assembly, so the gearbox and the brake, and this can move in and out 2 millimeters. I have it locked right now with a dimension, so I can't drag it, but moves in and out. And so the next part of the assembly is the brake gearing. So let's turn on, let's see, start with this. There we go. I'll just go through all of it. Let's turn this plane off real quick. So this is a Gobilda brass servo gear here that is attached to a servo, and it drives these gears, which should either be 3D printed out of nylon or another durable plastic, or possibly using a resin printer or something, an industrial printer. and they drive a screw. And so let's cut this in half now so we can see the inside. There we go. So they drive this screw here that moves the actuator in and out. And so because you're driving a screw, it's actually creating a pretty high thrust load on this shaft here. So, and this gear. So to counteract that, this is an angular contact bearing as listed in the inventor bearing thing, or at least it can take lateral loads like this. And then we have a PTFE thrust washer here. So I'm not sure how well the thrust washer would actually hold up to this load. Have to do a little more math on that, and it'd also be good if I ever did make something similar to this just to play around with that to make sure we don't need a roller thrust bearing or a needle bearing. And then we have this gear in the middle, which is just an idler. And so the neat thing here is we have different heights. So this is actually bumped out a little bit and is a different color. And so this is part of the cover assembly, which I'll go over in a minute, and keeping track of rotation. So it's going to be essentially in form of optical encoder. And then lastly on this we have the Neverest mounting plate, which was heavily inspired by Sanford's mounting bracket he used on his version of in-wheel gearbox. I really like that C. And then just a pulley here and a timing belt, HTD 3mm, 6mm wide. And so that's the inside of the Mecanum wheel. So you have your gearbox and you have your brake that goes in and out. Now, going back to this, I want to talk a little bit about the cover assembly. Oh, can I open this? Yeah, okay. So, here it is. We have a Go Build a Servo, probably high torque, and then a 3D printed enclosure. And so the neat thing is we have this little custom encoder, in a sense. It's an optical distance, a really small optical distance sensor. I have a couple of these from inkjet printers, and they're all the same. And they have a really high resolution, so they can detect really small distances. And so the idea is that it would detect the distance between the base of the gear here and this boss here. And so you could use that to count rotations and make sure your brake system is going in the correct amount and not going in too far or not going in far enough to break the wheel. And so here is a full wheel assembly. It is just screwed to the ring gear of the gearbox. And there'll also be some JB Weld or epoxy or something to fill in these holes so we don't have grease spilling out of our wheel. That wouldn't be good. You'd contaminate the field elements. Here's the Neverest motor, and that's kind of the end of the wheel assembly. So next I'm going to talk about our odometry modules, which I should be able to open up here. The unique thing about these modules, or the new thing, I don't know if unique is the correct term, but it uses an AMT10 encoder. And so I was actually looking at these a while ago. I noticed some other people on the FTC Discord server have been looking into them now too, and they do look like pretty sweet encoders. There's a short series and a long series. I just put on the long series, the 102 series, right now with a 38mm wheel, which looks a little sketchy. We might move this up to a 50mm Omni wheel, and maybe swap out for the smaller encoder. It's just the Nexus plastic Omni wheel, boring frame here, pretty regular. Ooh, the bearings didn't show up. Huh, weird. And then it just uses a boring old extension spring to be sprung into the ground and pushing into the mats. So that's our odometry module. And then we have the frame, and we have these custom shaft beams because it's VCC, and we don't actually have to manufacture them, but they're a custom length, 69 millimeters in out, and the pods are from outside of plate to outside of plate, 75 millimeters with 3 millimeter thick 7075 aluminum. Here we have some thicker aluminum cross braces. Frank made these cool holes so we can swap out to different positions, and we may add a back brace depending on the game. And that's really nice pocketing and color on the wheels. Credit to Frank, he did the renders and stuff too. I'm not very good at renders, but looks pretty cool. And so that is our locking Mecanum Drivetrain and kind of how it works and the history of the concept, how we came up with it, and we're looking forward to the VCC competition. And we hope this shows that a locking Mecanum Drivetrain is something that would be technically difficult but feasible at an FTC scale, and maybe someday we'll see a simplified version of this, maybe without the whole in-wheel gearbox thing, as a prototype, and maybe some team will use some of these ideas and a future drivetrain to actually be used in FTC. The next steps are going to be making a design that'd be easier to prototype, and then eventually making the real module. And so I guess the question now is, what are your thoughts? What do you think? Is there anything we could do differently? Do you have any suggestions or criticisms? Any other ideas on this? What do you think of the whole strategy of using a locking Mecanum wheel? Thanks for watching, and if you're competing in the VCC, good luck. See ya.